Hi everyone, I'm Hendrik Waldner and this talk is about consistency for function encryption, which is joint work with Badertscher, Aggelos, Kiayias and Markulf Kohlweiss. Let's start with some motivation. Let's consider the setting in which we have a database owner Charlie, and now we want to allow another party Alice to store some photos in this database. Furthermore, we want to allow a law enforcement agent Bob to search the photos stored in the database for a specific suspect while preserving the privacy of Alice. This means that we only want to allow Bob to learn if a specific photo contains the suspect or not and nothing beyond that. Next we are going to see which cryptographic primitives we can use to achieve this goal. The first primitive that could be useful in this setting is public key encryption. In public key encryption we have a setup generator Charlie that outputs a public key to Alice and a secret key to Bob. Alice can then use the public key to encrypt the message X and send it to Bob. Bob can then use the secret key to decrypt the ciphertext and to recover the complete message X. The problem with this notion with respect to our use case is that it does not allow for any fine-grained access control over the encrypted data. Bob can either decrypt the whole ciphertext or nothing. To allow for fine-grained access control over encrypted data, the notion of function encryption has been introduced. In function encryption, the setup generator outputs a master public key and a master secret key. The master public key is used in the same way as the public key before to encrypt the message X. The master secret key, though, is not used to decrypt the ciphertext, but to generate functional keys using a key generation procedure and a function f. If such a functional key is used in the decryption procedure, Bob receives as an output the function f associated with the functional key applied on the encrypted message. This notion gives us the desired access control that we need in our motivational example. Before looking into how the primitive can be deployed in this setting, we take a closer look at the security definition of function encryption. The security definition of function encryption aims to protect against a malicious decryptor. This means that it is ensured that a decryptor cannot learn more about an encrypted message than what is leaked by the functional keys it has received. In cryptography, security is usually captured using a game where an adversary interacts with a challenger, and if the probability of the adversary winning the game is below a specific bound, we say that the scheme is secure. In the first step of the security game for function encryption, the challenger samples a random bit B and executes a setup procedure to generate the master public key and the master secret key. In the next step, the challenger sends the master public key to the adversary. Afterwards, the adversary can make a functional key query by submitting a function f to the challenger. The challenger then generates the functional key according to the submitted function and returns the resulting functional key to the adversary. The adversary is allowed to make as many functional key queries as it likes. After the adversary has finished its functional key queries, it makes its challenge query by submitting two messages x0 and x1. The challenger then makes use of the random bit B that it has sampled in the beginning and generates a ciphertext by encrypting the message xb. This ciphertext is then sent to the adversary. After the adversary has received the ciphertext, it is again allowed to ask functional key queries. After the adversary has finished its functional key queries, its goal is to determine which of the two plaintexts x0 and x1 has been encrypted by the challenger. To indicate its guess, the adversary outputs a bit B', and if B' is equal to B, then the adversary wins the game. To make it non-trivial for the adversary to win the game, we need to enforce an additional restriction on the functional key queries asked by the adversary. Right now, the adversary could obtain a functional key for a function f such that f of x0 is unequal to f of x1, which would allow the adversary to directly determine which of the two messages x0 and x1 has been encrypted. To prevent the adversary from doing this trivial distinction, we only allow it to submit functional key queries for functions where it holds that f of x0 is equal to f of x1. Coming back to the motivational example, we can now apply a function encryption scheme to equip Bob with the desired access control. In more detail, we let Charlie generate the master public key and the master secret key. The master public key is then sent to Alice and a functional key that detects the requested suspect is generated for Bob. The security of the function encryption scheme here guarantees that the privacy of Alice is protected and that Bob only learns if a photo contains the suspect or not. Now one might ask the question, what about other malicious parties? A malicious Alice, for example, might be able to generate a ciphertext that contains the same information as a properly generated ciphertext, but for which Bob's functional key does not yield the correct output. To prevent these kinds of attacks and to protect against the malicious Alice and, as we will later see, also against the malicious Charlie, we introduced the notion of consistency. The first of the three consistency notions is input consistency, which protects against a potentially malicious Alice. As in the case of security, we use a game to define this notion. The first two steps of the game are the same as in the security game. The challenger generates the master public key and the master secret key, and sends the master public key to the adversary. Afterwards, the adversary is allowed to ask several functional key queries. In the last interaction, the adversary outputs a ciphertext. It is then checked if the decryption behavior of this ciphertext is explainable, which means if there exists a plaintext that leads to the same function evaluations. The challenger checks this condition by decrypting the ciphertext using all the functional keys that the adversary has previously received, and by computing the intersection of the preimages over the different functions corresponding to the different functional keys. If the intersection is empty, then there exists no plaintext that explains the decryption behavior and consistency is broken, which makes the adversary win the game. Additionally, we have to consider the case where the ciphertext is not decryptable at all. In this case, a consistency attack only happens if the decryption procedures disagree on the fact that the ciphertext is decryptable. In other words, consistency is only broken if some of the decryption procedures yield a valid output and some don't. Next, we are focusing on the case of a corrupted Charlie. Here we want to prevent Charlie from generating misleading functional keys. Such misleading functional keys could, for example, make Bob think that the suspect is not contained in the picture, even though it is, and the other way around. The notion that focuses on a malicious Charlie is the notion of setup consistency. In this game, the adversary first outputs a master public key, a function, a functional key, and two plaintexts. The challenger then encrypts both of the plaintexts and runs the decryption procedure using the functional key sent by the adversary on both of the generated ciphertexts. The challenger then checks if the function evaluation of the plaintext using the function output by the adversary is equal to the functional decryption outputs. If this is not the case for at least one of the two decryptions, the adversary has caused a consistency attack and wins the game. In the case that the decryption procedure does not yield a valid decryption output, a consistency break only occurs if the other decryption procedure succeeds. To allow for this check, the adversary needs to output at least two plaintexts. In the case of a malicious Alice and Charlie, the adversary has the combined adversarial capabilities of the two previous cases. It can create different keys that, together with maliciously generated ciphertexts, yield any desired decryption output. The notion that prevents these types of attacks is the notion of strong input consistency. The strong input consistency game is a combination of the input consistency and the setup consistency game. The adversary sends a single message to the challenger which contains the master public key, a set of functional keys together with the corresponding functions, and two ciphertexts. The challenger then computes the decryptions of both of the ciphertexts under all of the different functional keys and checks if there exist plaintexts that explain the decryption behavior of the two ciphertexts by computing the intersection of the preimages over the different functions corresponding to the different functional keys. If for at least one of the ciphertexts the decryption behavior is unexplainable, the adversary wins the game. This concludes the description of the consistency notions. In the full paper, we present additional results. We prove separations between consistency and existing security notions to show that our notions indeed capture something new. Furthermore, we analyze existing functional encryption schemes and show how they can be modified to achieve consistency. Additionally, we present black box compilers that turn any functional encryption scheme into a consistent one. These compilers are based on the work of verifiable functional encryption and are mainly relying on non-interactive zero-knowledge proofs and non-interactive witness indistinguishable proofs. Finally, we also present an analysis of our notions in the UC framework and show that we can extend the results of Mudd and Maurer from 2015 by also protecting against a malicious Alice and/or a malicious Charlie and not only against a malicious Bob. Thank you very much for listening.